Alright, so let's look at our first example. The graph below shows the growth of the Mexico City metropolitan area from 1970 through 2000. So those are the years that this that this data models. In 1970, the population of Mexico City was 9.4 million, and by 1990 it had grown to 20.2 million. Okay, so those are important data points that we need to identify. So I'm going to annotate the text. 1990 goes with 20.2 million. So these are going to be like our initial amount. So I'm going to call that A naught, and I'm going to call this A. So they also gave us a little graph here, and then the question is asking, find the exponential growth function that models the data. There's some other questions after this, but first let's just find out what the function is. So there's several things that we want to think through in order to get the answer here. So looking at the guiding questions, our first question asks, what's the form of the function that we use for exponential growth or decay? Well, you might have to look back at those previous slides, but it's always some future amount equals some starting amount with base e and then raised to the kt, where k is our rate and t is time. So we're always going to be thinking about that format. Now we want to take our numbers and think about plugging them in. So our T0 is 1970, and the amount that corresponds to T0 is 9.4 million. And can we substitute our knowns into the formula? Yeah, we can. We have 4 knowns, and we can go ahead and plug those in. So some future amount here, 20.2 equals, and then our starting amount, 9.4. Base e, remember that's just a number, it's not a variable. They did not tell us the rate, just like in real life. Nobody would tell us what the growth rate is. They would just give us some data, and we would have to figure it out. And then we have to figure out, what do we plug in for t? So we want to think about what the time span is here. So we're going from 1970 to 1990. So that means our time here is going to be 20 years. So I'm just doing 1990 minus 1970. So I'm going to plug in 20 years. So we're finding out what the exponential growth rate is from 1970 to 1990, because that's the data points that we are using. Okay, so we have our knowns plugged in to our format of the equation, and now the only thing that we don't know is k, which is good because we can solve for that since we only have one unknown. So just think about how we solved our exponential equations before. We started by isolating the base. Our base is e, and right now it's being multiplied by 9.4. So let's isolate it. Let's divide. So I get 20.2 divided by 9.4. I'm going to have to put that in the calculator and figure out what it is. That's going to be equal to base e raised to the k times 20. Okay, so I want to solve for k. Right now it's stuck up in the exponent. I see that we have base e. So one thing that we could do is take the natural log of both sides of the equation. Okay, that will keep our equation balanced, but it will let us take this exponent down to the front using our properties of exponents. So I have ln of 20.2 divided 9.4. Okay, that's going to be equal to, I'm going to switch the order here since it's just multiplication. I'm just going to call it 20k times natural log of e. And then when we simplify this, a natural log on base e, that's it. Well, natural log is base e. So when I do it to base e, I just get 1. So that's sort of an easy simplification. And 20k times 1 is just 20k. So we're almost there. The last thing that I need to do is isolate the k. Right now it's being multiplied by 20, so I want to divide by 20. Okay. So I'm going to put all this into the calculator that's on the left hand side, and then we will know what k is equal to. Okay, so I got 0.03825, and I'm just rounding. I got 5 decimal places, so that's sort of a lot. So that is my rate. Now, if they had asked me find the growth rate, this is what I would be looking for. Or if I wanted to express it as a percentage, I could do that. So later on in a worksheet, I'm just going to ask you for the k value. So this is basically like 3.825%. So that's how much the population's increasing by. But of course, in our formulas, we're going to use the decimal. So we're to our last step. We basically have all the information we need in order to actually write a function. So let's go ahead and do that. We're going to leave a as a and not plug anything in, because this would be something that we would give to somebody so that they could make predictions. And then our starting amount is 9.4, so we're going to plug that in. Base e, and then our rate times our time. So I'm going to put 0.03825 times t. So that is our exponential growth function for part A. Looking at that second part on the next slide, it's the same setup, but it should actually say part B. And they want to know, by what year will the population reach 40 million? Okay, well, we did the hard part, which was actually just writing the equation. Let's put that over here also. Okay, so I have my function that we found to the right. Our rate is positive because our population is growing. If our population were decreasing, that k value or that rate would be a negative number. Okay, so they want to know what year. So we're going to be solving for t. That's the one that we don't know that they're asking for. But they do give us a little bit of information. They want to know when the population will reach 40 million. So that's going to be our a value here that we plug in into our equation. So let's go ahead and do that. I've got 40 equals 9.4 e to the 0.03825 times time. So we know how to solve these exponential functions. We start by isolating the base. Right now our base is being multiplied by 9.4, so I'm going to go ahead and divide by 9.4. Okay, so that's going to give us whatever 40.9.4 is. That's going to be equal to e raised to the 0.3825t. So since we have base b and we also want to solve for t, which right now is stuck up in the exponent, we're going to go ahead and take the natural log on both sides of that equation. And what that allows us to do is use our power property in order to bring our exponent down is a multiplier to the ln. And then also, we're going to do the ln on e, which is just 1. So I'm going to come over here. I've got ln on 40 divided by 9.4. Using our power property, I get 0.03825 t times ln of e. Simplifying that, that's just 1. So anything times 1 is just itself, so I can just stop writing it. And then last step is that I can divide both sides by 0.03825. And the reason why I'm doing that is because we are trying to isolate the t. So that is the number that's multiplying t right now. So that means after that cancels, we are going to get our answer. Time is 37.886. Okay, so think about this in context of our problem. They want to know what year the population will reach 40 million. And we got t equals about 38. I'm actually probably going to round up to the nearest year for my final answer. So we want to convert that to the year. So just recall that our T0 was 1970. So we're going to be adding basically 38 years, I'm rounding up to the nearest year, onto that 1970 in order to find out what year we're actually talking about. So that would be 2008 is our final answer. So 2008. And then I always want to think about, does my answer make sense? And what we can do is just plug in 38 into our formula and see if that works out. But 37 years seems reasonable given that it's growing at almost 4% a year.